Good morning, everyone. Yeah, so wrote this brief recap of what we did yesterday. So covered a lot of ground. So we talked about the relation between causality and analyticity in the frequency upper half plane, and hopefully convince you that this sort of abstract mathematical concept is really important when you think about Fourier transform back to the time domain in order to get sensible physics. And then we also discussed that in quantum field theory, we have a sharp statement of causality, which is that commutators vanish at space-like points. And that motivated us to look at amplitudes where the operator ordering is changed compared to the usual one, so that we can actually compute these commutators. And we described some classification problem, and some of the things that came out were the sort of funny objects that are we actually familiar with. So here, it's not time order because these A operators create stuff in the past. Here we do some measurement in the future, and then we evolve back in the past. But if you think carefully about this, this is actually what we do all the time in quantum mechanics, where we calculate a probability, which is a square of a wave function that comes from evolving the future. Then the part that goes back to the past is just the complex conjugate side of this cross-section. But that type of quantities specifically is an inclusive cross-section, because you can insert a complete basis of state here, and it's summed over. And these are these unobserved states that you have to sum over here. They are unshelled states. So what you're really computing with this sort of object is a cross-section for, say, one tube producing particle 3 with some momentum plus anything else, okay? Which are nice observables. And when you think about it also, you don't have to organize things in terms of number of operators. You can have things that are actually linear in the fields, like there's more sort of funny things that actually appeared in Donald's talk and would appear in Donald's future lectures that give you, for example, a waveform that measure the gravity or electromagnetic field that results from a collision. Expectation value of something in a state that's described by what you throw in. Okay. Good reference for causality in the S matrix are these lectures by Sebastian Misera. We have given those yesterday. The story about classification of observables is in this paper that we wrote last year with Mathieu Giroux, who was in the audience, and Sebastian Misera and Ophi Slotir. And the connection between all this story and crossing, which is our next and final step today, is actually a result from this other paper. Okay? So the sort of general understanding of crossing for 2-2 scattering is very old, but the generation that we present to higher points is the new formula. So before we move to crossing, it would be handy to have at least one example of a calculation of this thing, at least one diagram. Donald will describe many more. Then we need this one. So suppose we have a particular diagram that contributes to an amplitude, say this one. Say a 5-point amplitude, 1, 2, 3, 4, 5. And the question is, how much does it contribute to this waveform? Let's call it star. Okay. So what's the contribution of this particular diagram to this waveform? The key message of this example is you can compute this diagram by diagram. You can compute this these funny observables diagram by diagram. So let's see how this works. The idea is that you have to match all the way of cutting through this diagram, separating between the amplitude and its complex conjugate, that match the blob pattern. Okay? So we need to draw all cuts that match the blob pattern. So this is a course in advanced blobology. So how do we do that? So there's kind of a, yeah, before I go with the obvious one, maybe just start with the non-obvious one, which is that whenever we have this blob, it's actually going to be important to remember that an amplitude always has a disconnected part. So when we write, and what we wrote, what appears and is observable on the left is really the S matrix, because that's the thing that evolved from the past to future. But this S matrix blob always has a part that's nothing happening, plus a part that's the connected amplitude where something actually happens. Okay? So in particular, these blobs, there are many options. So the blob pattern that we're interested in can have part with S dagger and 1, 2, 3. There's a part where nothing happens. And 4, 5 just go straight without using the S dagger blob on the right. And there will be a term with where you actually, sorry, it's not S dagger, it was S on the left. Sorry, S. And there's a part where you actually use the scattering, the rescattering on these two guys on the right-hand side. And the connected part of S dagger is minus I M dagger. I'm trying to not hide any i's into definitions nor so that we can actually follow the signs. Okay, so there are these two terms, and that's going to be a connected amplitude. And in principle, you could have imagined terms where you, it's actually hard here, you could, if you try to have a disconnected part for S, you could imagine having 2 going straight to 3, and maybe 1 going to 4, 5. But this is, well, this doesn't make sense for two reasons. First of all, this particular one is stable, so that decay does not make sense. And it's also going to vanish if we assume that 2 and 3 are not forward, which we normally do when we measure the radiation. So this vanishes for 2 reasons. And there's for, stability. Of 1 and P2 not equal to P3. Okay? So it vanishes for 2 reasons, so we're not going to ignore that. But we have to match this diagram into these 2 possible blobs. And well, matching it to the first blob is very easy. We just get the usual amplitude. And in this case, that will basically give a bubble integral that's a function of S12 with, say, a plus epsilon, the usual bubble, times bubble of S45. Okay. It will be massless or massive. That's not, here, I'm not going to write the explicit formula, but it's some one loop bubble integral, right? So this is usual amplitude. Then, what other blobs can we write? So if we try to match this thing at the top to this pattern, we need a connected amplitude where 4 or 5 meet at some vertex, do something, and then on-shell states. And this can happen if I cut through this bubble on the right. So there's a term that look like this, where here this is complex conjugate and this usual amplitude. In this term, these 2 propagators are on-shell. So this particular diagram gives the bubble of S12 times the cut, this integral, this on-shell integral, which you know by the Katkowski rule is equal to the imaginary part of the bubble. In fact, the signs work out so that it's minus 2i times imaginary part of the other bubble. Okay, yeah, I will try. And if I get smaller again, please remind me. Yeah. The important thing is the subscript here, S45. So something nice happens when you do this. You have a function plus minus 2i, its imaginary part. So it's actually just giving you the complex conjugate of this function. Okay. Which you can also rewrite as the bubble with the usual I epsilon in the S channel times the bubble with the opposite I epsilon in the 4-5 channel. Okay. And when you think about it, the fact that we just reverse the I epsilon in the 4-5 channel sort of makes sense from the time domain picture of this thing. Normally, the I epsilon is telling you that positive energy excitations propagate forward in time. But there we're going back to the past for these two guys. So that's why we flip the I epsilon. So that result makes sense. And yeah. And there are no other graphs. This is it. This is the answer. So why is there no? Why don't I draw this guy, for example? It will be the other natural cut for this process. Why does it not fit the blob picture? You have to train your eyes a little bit. Yeah, the picture is here. Why does this cut at the bottom not fit this picture? Yes.
Actually, sorry, yeah, actually wanted to ask something else.
Good.
What in passing from the complex conjugate to the minus I epsilon prescription,
Yeah.
you assume that the only thing that contributes to the imaginary part is the plus I epsilon prescription. So in the sense that you're saying that like the complex conjugate of the amplitude will just complex conjugate
this is a theorem known as a Kotkowski rule, that the imaginary part of an integral is can be computed in terms of on-shell integrals. Yeah, this relation.
Okay.
Here I've used Kotkowski secretly.
Okay.
Thank you.
And in general, it's always true. There's nothing like spoiling this property.
Yeah, in general, you have to sum over all possible cuts. That will give you the imaginary part of an amplitude.
Okay.
Yeah. Thanks for the question. Yeah.
So
yes.
I guess the reason that doesn't match is because 3 has to be outgoing from the left blob.
Exactly. So 3 here absolutely has to be emitted for the amplitude. 3 cannot be emitted from the complex conjugate amplitude. Thanks. Yeah. So this guy is not there. 3 must be emitted from the amplitude. Okay. So that's why we're done. So we'll store these results. It will come handy later on. So now we're ready to discuss the relation between these concepts and crossing symmetry. Oh, actually, I want to say one thing more before. So we'll speed that up. And this will move. So something else, something I want to mention that's useful when you calculate these cut integrals is that it's quite useful to have rules for computing this matrix element dagger. So this is essentially a version of the Kotkowski rules, Kotkowski-Feynman rules. So essentially, every time you have a vertex that is on the amplitude side, we'll say that's the usual vertex. And every time you have a vertex that's in the M dagger side, we'll draw it with a round circle. And say that's going to pick an extra minus sign from the usual vertex. And this minus sign usually has to do with conjugation because vertices have I in them. But I'm going to write them with minus sign to avoid star signs. Okay? So for example, yeah, okay, I should have turned it above, but we're not. Yeah. So you should see a big circle on the top right figure. Okay? And then you have the propagators. The propagator that joins two standard propagator will be the usual. So for example, minus I over p square plus m square minus I epsilon. A vertex that join two vertices on the complex conjugate side of the amplitude will be minus the usual with minus I epsilon. For example, plus I or p square plus m square I epsilon. For scalar field theory, it's just complex conjugation, but I'm trying to write it in a way that doesn't involve the star symbol because it would get confused when you compute things with fermions. These rules are always valid with the minus sign. Okay? And the last propagator we need is this propagator that go from amplitude to the complex conjugate. And this happens when you have on-shell particles that cross a cut. So this would be cut. So this would be basically, this thing will be 2 pi delta function of p square plus m square. And when you have a cut, the energy always you're producing on-shell particle, they have to have positive energy. So there's a step function of p0. Okay. I will also keep this board for future reference. Okay. So we can use these rules to calculate any diagrams with a cut in it. Okay. And that's essentially what the picture at the top. Maybe it's worth taking 3 seconds to decorate it. This is well designed. So these are normal vertices, and this is a round vertex. So you see that these two propagators are cut, but these ones are the usual time order one. Okay? So if you apply these rules, you will basically be computing this m times this m star with on-shell particles in between. Okay?
Simon? Sorry, can I ask you a question?
Yeah.
So you were always considering just a one loop process with this external like attached leg, right?
Yes.
Okay. And you were always from the get-go, you were using the Kutovsky rules to represent the squared amplitude.
Exactly. Yeah.
I see. Thank you.
But these rules hold for any diagrams. And yeah, you just have to cut the diagram in all the possible ways that fit the blob picture. So for example, an external leg attached to the amplitude side, it has to be uncircled.
Thank you.
So crossing symmetry. So we're going to look at these commutators. Yes.
I have a question. So why are we summing the uncut and the cut diagram with equal contribution, or is there some?
Yes.
In
this particular case, what told us to do that is just this blob picture. It was identity and not identity. In general, we can derive something like a LSD reduction formula for these two things, which will tell you that you have to include that the 4, 5 vertices can be either circle or not circled, and you have to sum both cases. So
and it's always going to be like if there were 5 different ways to cut it, they will all be summed with equal contribution to.
Yes, the restriction in this case is that the vertex, the leg 3, has to attach to an uncircled vertex.
Okay.
So if you sum over all circlings with that restriction, you would get the right answer.
Okay.
And that is something that follows by writing carefully LSD reduction formulas for this type of objects. But yeah, think about this later. Thanks. Other questions? The thing that are actually useful for these sort of arguments is not just the commutator, but the so-called retarded commutator. So when introduce this object, that's a field at x1, field at x2, times a step function that's set x2 in the future of x1. That we're going to call the retarded function with arrow 1 goes to 2, that 2 is in the future of 1. And this object actually is Lorentz invariant. There's a step function of time, but because it vanishes for space-like momentum anyway, space-like separation, sorry, anyway, the step function makes it cancel it and cancel its forward past light cone, and this is supported in the future light cone. X2, mu, write a funny notation for the X2 in the future light cone of X1. Okay. Well, it's weird, it just looks weird. It's meant to be a curly greater than equal greater sign. Okay. This object has nice properties. So I will state a few facts that are relatively easy to prove, and then I will say what's the tricky step in the argument. So the fact that it's supported at positive times means that its Fourier transform has nice properties. So in momentum space, so if I take this function R1 to 2 and evaluate it with some complex momentum, P1 mu minus IQ mu, P2 mu plus IQ mu. So roughly Q is conjugate to the separation between 1 and 2, where all of these things are real. Then this function is analytic in the upper half frequency plane for Q0 greater than 0. In fact, it's analytic in the bigger region, which is the Lorentz invariant version of the statement. That's going to be useful as long as Q0 is in forward light cone, is in the future light cone. Okay, future inside the is future time like maybe like this. Yeah. Okay. For Q mu equal future time like. So it's analytic if you add some kind of imaginary part with the correct sign. Okay, and that is just from the support properties of. So for a transform a function that vanish for negative time, so it has its property. The other fact that is useful is that when we take in momentum space, when you take the momentum to be real and close to the mass shell, we can relate this operator to creation and annihilation operator of particles by some LSZ type argument. Okay? So this is LSZ for real P mu. It tells us that this function, well, times P1 square plus M square and P2 square plus M square, the usual thing you multiply by in the LSZ reduction formula. When you go on shell, reduce the creation and annihilation operators. And I will not go to the derivation of this, but you can sort of guess the result. So the important thing is that when these fields go on shell, they go to infinity. But we're forcing 1 to be in the past of 2. So 1 is going to go to past infinity and 2 to the future. So 1 goes to past infinity, so it either gives A daggers or A. This one gives either B dagger or B. And whether it's A or A dagger depends on the sign of the energy. So you get A dagger, but the commutator still stays there. So you get the commutator of A1 dagger with B2. That's if the energy are such that 1 creates a particle and 2 absorb the particle. And you get A1, comma B dagger 2, if I reverse these inequalities. If P2 is 0, 0, okay, so the sign of the energy determine which one is created. You can also have a situation where they both have the same signs, but I just put dot, dot, dot. This will not actually matter for the argument today. So these are the 2 cases that we need. Okay. So these 2 are the key facts. They tell us that we have an analytic function, schematically, which on the positive real axis reduced to a certain amplitude, and the negative real axis reduced to a different amplitude. We're going to use that to get crossing. So the last ingredient we need is some parameterization of the momenta. Okay? So let's write down some explicit parameterization so we can be very explicit about what crossing means. Okay? So in like cone coordinates that were used also in some of the earlier lectures, we're going to use a complex variable z, which basically is a boost that rescales the plus and minus component of P1. And same thing for P2. Here's 1 over z, P2 minus, P2 perp. And we have to start from a frame in order to conserve momentum. We have to start from a frame where P1 plus P2 is a purely transverse. Frame where P1 plus P2 is 0, 0. Oh. Okay. Otherwise, this will not preserve momentum conservation in the overall process. But if P1 plus P2 add up to 0, then P1 mu plus P2 mu will be independent of Z. Okay, and this is kind of like a boost. Z we can think as a boost factor. So the schematic picture is the following. In the Z plane, which is going to turn into like some Mandelstam invariant momentarily, in the Z plane, here we have a certain amplitude, and here we have analyticity. I'll put a question mark, what we expect analyticity. And here we have something like this commutator, A1 dagger V2, and here we have A1 dagger, sorry, A1 V2 dagger. We have this other process. So we're going to be able to relate process where we create particle 1 to a process where we absorb particle 1. Okay. And maybe I can draw a little sketch here. So this is really making contact with this figure, that this cartoon that we had last time, that if we put particle 1 here and particle 2 here, we can relate a particle going from one to the other to an antiparticle going the other way. Okay? So we're going to relate those two processes by using analyticity in the upper half plane. Now there's an issue. So if Z in the upper half plane, then the imaginary part of this guy is the correct sign. But we need the imaginary part to be in the future like cone, so it means that the imaginary part of P2 minus should also be positive. So here we start with these two things are positive. P2 and P minus are positive. And the issue is that the imaginary part of 1 over Z, P2 minus, is not positive when the imaginary part of Z is positive. In fact, it's exactly always in the lower half. This is bad. So we don't quite have the analyticity. And this is why proving crossing is tricky. So this issue has been, it's been proven that this actually doesn't matter for 2-2-2 scattering. So it's proven to not matter for 2-2-2. But the proof is hard. And we have not proven this for higher points. Instead, what we will do is we'll just take Z to be large and hope for the best. Okay? We hope that when Z is large, this minus component will be very small and will not matter for anything. Okay? So this is the tricky part of the argument. It would be nice to do better than that, but we can check whether it gives good predictions. So these are the ingredients. What do they give us? See now, let's say something else. So when the energy is very large, so that basically means that I'm boosting the particles that I'm crossing, so they have very high energy. And let's assume that they have the highest energy in the problem. If they have the highest energy in the problem, then I'm not going to be able to absorb this energy before I create it. So this will just become, the commutator becomes a single term, B2 integral 1. And I could evaluate it in some states X and Y. And here on the side, I will get, maybe I should draw bigger, I will get just Y times B dagger 2, A1. So you have to create this huge energy before we absorb it. So the commutator becomes single term. And this would have a minus. So the way we propose to think about crossing at higher points is that it's a relation between this process and this process. So let me draw it to summarize. So if we start with some in-state X, and you scatter it against some particle 1, that's the process on the right. And here, so particle 2 and Y. So this is this, maybe I can give you a roadmap. This is the A process. This is going to be the B process. This is the A process. What we're doing is that we're going to flip the signs of the energies of particle 1 and 2. So we're going to do a crossing that take particle 1, which is incoming, to be outgoing. We have a large energy. That's going to be our crossing move. And that, what does that give? Now you see that because it's a commutator, we get a funny operator ordering here. So this is the same having an S, an A dagger to S dagger, and then here there's again the evolution here, S. So there's S, S dagger, S. So when we turn this into amplitudes, it gives the following. that will stagger. One now is there. Two is there, so we cross those legs. And now there's an S blob acting on X. And there's S blob acting on Y. And put overall minus. This is the general crossing equation. A general crossing equation. Okay. So the idea is that we can, if you want, you can forget the arguments before. But the important thing is that what we predict is that if we start from this process and follow this particular path in the z variable, you will land on this particular amplitude. That's what we obtain by thinking about these commutators. That's the main sense. And maybe a quick comment is that for 2-to-2 scattering, if you think about this as a 2-to-2 scattering process, then X is single blob. X is single particle. So X and this S, that just becomes trivial. So we can drop the S's on the outside, drop the S's, and you get the usual relation between the amplitude and its complex conjugate that we talked about yesterday. So it works nicely. So this formula reduces nicely to the usual one for 2-to-2. But in general, if you apply it in a higher point amplitude, you would have to deal with these extra blobs, which we now know how to deal with by adding little cuts. Okay. So we'll do an example of this. Any question before we do the example? It's a bit fast, but hopefully the example will help. Yeah, there's overall minus sign. Yeah. And this minus sign works nicely if you just recall the case of 2-to-2. On the left, you have I times m. On the right-hand side, you have minus times minus im dagger. So it kind of nicely cancels out when you rate the amplitude and its complex conjugate. Okay. Yeah. Somehow the formulas are easier to understand in terms of S than amplitudes. Okay. So I'm going to illustrate this on essentially this example we've done before. And we'll start from this process. Let me do it properly. I have to first draw the two bubbles. And I start with this process. Okay, and the orientation of a leg tells you, thinking about the time going to the right, the orientation of this leg tells you that 2 is outgoing and 3 is ingoing. Okay, so that's our process. And we're going to cross 2 and 3. Okay. This expression is the bubble in the S12 channel times the bubble in the S45 channel. And the S45 channel is a usual amplitude, so it has a usual plus I epsilon. And the S12 channel, we don't actually care about the epsilon because this channel is space-like. There's no imaginary part. Right? It's pretty real. So I epsilon not needed since space-like. Okay, S12, that's it. Okay. And now we have to think about how these invariants continue, all the various minus time invariants in this problem, and then to continue under this path. Now it's with P2 and P3. So I'm going to draw a complex plane with various invariants, and we see what they do. Yeah, maybe the simplest invariant to start with is S24. S24 is an invariant between two outgoing particles, so it starts time-like. And S24 goes like P2 plus times P4 minus, where each of these is positive. Remember that P2 plus is supposed to be huge, so I can approximate the invariance in this fashion. Okay. When I do this crossing path, from crossing path is this arrow, and in the z plane, that just takes this invariant to the left here. So S24 after the crossing would be here. Okay. That's a crossing path. And this is the usual way you would cross some S-channel variable as in 2-to-2 scattering. Okay. Now, okay, S24 is not the variable we care the most about. It doesn't appear in these formulas. S12 is one we care about. S12 starts here. Doesn't matter which side of the axis it is because the cut's on the right. S12 starts here. And similarly, it's proportional to P2 plus, P1 minus. So it rotates in the same counterclockwise direction. That means it ends up here. Okay? So something that starts space-like ends on the wrong side of its cut. And finally, the last thing we need is S45. But our crossing move doesn't do anything for particles 4 and 5. So this is trivial. Starts time-like and stays there. So this is our crossing move. Erase this. So after our crossing move, we end up with the bubble in the S-channel, S12 channel on the wrong side. Minus I epsilon times the bubble in the S45 plus I epsilon. Okay. This formula and this diagram illustrate why crossing is subtle at higher points. Because you see, if you start doing some continuation, some invariants end up on the wrong side of the cut, and some invariants stay on the correct side. And this phenomenon was observed already in the 60s and 70s when people tried to generalize crossing at higher points. And they land on this weird object. And then what they try is, the first thing they try to do is to use Cutkosky rules to get rid of this wrong side cut. Use discontinuity formulas and so on. Okay. What we're adding to this story is that, well, we have an interpretation for this thing. This thing is supposed to be exactly this blob picture, where you tack on this S to the passive particles. In fact, in this case, I'm going out of space. Maybe I will erase the 2-to-2 case here for 2-to-3. If I cross 2-to-3, I look at this amplitude for 2-to-3, and I swap 2 and 3. What this formula predicts, let's look at the prediction. I swap two guys. I'm supposed to get this big blob will turn into a S dagger. These two guys will be swapped. Actually, to match the picture more closely, it's okay. Yeah, I should probably put a 3 and a 2. Let me put a 3 and a 2. Sorry about that. 3 and a 2 would be easier to follow. 2 and a 3. Here, we're supposed to tack a blob on the one leg, but it's a stable particle, so nothing happens. But here, we have to tack a blob on these two particles, 4 and 5. So that's a prediction of this formula. But this is exactly what we calculated at the beginning of the lecture with some foresight. In fact, what we calculated at the beginning of the lecture is a complex conjugate of this. We have the S in the S dagger swapped. So this is exactly the complex conjugate of what we computed before. You can see the formula at the top of the line, top of the board. It matches precisely. So it works. We can be proud of ourselves. Yes.
After we do the analytic configuration,
Yeah.
After we do the crossing, why wouldn't S12 go to minus S12?
Ah, exactly. Well, yeah. Yeah. It happened to be a negative number. So look at, yeah, it's better to look at the picture. So it started a negative number, it ends up a positive number. So it's true that it's sign flipped, but I don't want to put minus signs in this formula. I just evaluated it in a different sign. So in this formula, S12 is less than 0, and this formula is greater than 0, but below the axis.
Okay, thank you.
Thanks.
Are we supposed to read a cut on this rightmost diagram here?
Exactly, yeah. So every time there's in this blob notation, every time this blobs are connected,
picture,
you always have on-shell states.
Perfect, thank you.
Yes, thank you.
Also, before, sorry, I didn't ask this before, but when you're taking large Z and you're relating one ordering of operators with the other ordering,
yeah,
then what property does it guarantee when you go to finite Z? Because you're taking large Z, so you're making an approximation, but when you go to finite Z, how do you maintain like the same operators and not include something else that you didn't want to? Okay.
I think a lot more remains to be understood, and it would be very great to have an understanding of what singularities can be close to real axis after you do this move. And yeah, there's a lot of interesting things to understand. Yeah, this was like the simplest guess that has a chance of working, and in simple examples, it works. That's what we can say now. We did some examples that are a bit less trivial than this, involving box and pentagon diagrams at one loop, for example. Yeah. But I think a lot more. Yeah, so maybe besides testing it, would probably be interesting to do some more application.
Simon?
Yes.
I don't understand then this picture that you're making where you write a general crossing equation.
Yeah.
At the left-hand side, I see no cuts.
Yeah.
And to the right-hand side, I see cuts. So
yeah.
when I read these, I think, okay, to the left-hand side, you have an amplitude, and to the right-hand side, you have like the square of an amplitude. But what does this
It's not quite the
mean?
square, yeah. So the first approximation of this picture, you should think about these two blobs as being the identity, completely disconnected. So to the first approximation, this is relating an amplitude to its complex conjugate. So this intuition is correct. But then with these blobs here, when you include this blob to be like 1 plus the amplitude, this is kind of correcting this picture by adding cuts. Okay?
I see. Thank you.
Yeah. And you need to add these cuts because, as this formula makes clear, you end up on the wrong side of some channels, but the correct side of some other channel. So this is why you need to patch it up. These S blobs are kind of flipping the sign of these I epsilons, roughly speaking, to bring you back to the correct side. Okay. Yeah. So this particular equation, so all the sum of the key steps of its derivation on this board, it came from analyzing the simplest commutator. And it's just one particular crossing equation we can obtain. And there's probably many more that are waiting there to be found. So some future direction or open question. It's probably more crossing move that makes sense. Some potential application that tough could be interesting is to relate, for example, scattering amplitude in different channels when you have analytic functions. What we see is that generally you go from one channel, you end up with an amplitude plus cut from the other channel. But maybe we explain that sometimes you can repeat this move and go back to something that looks like, again, an amplitude in some other channel. So this gives you a relation between amplitudes, even if you don't care about this finite object. So relation between analytic amplitude or maybe numerical amplitudes obtained with the differential equation method, because you can integrate differential equation along this path. Relation to different kind of objects. So perhaps in some cases, this could actually be a way to calculate these things. But maybe I should mention quickly that the fact that we have to go to very high energy to do this crossing is sometimes incompatible with things like classical limit that Donald, for example, wants to take. So it's not clear that this crossing this crossing may require you to go outside of the classical limits you're interested in, because crossing is a very quantum phenomenon. So there's no guarantee that you can actually find some useful way of computing what you're interested in. Okay? So I don't want to make too big promises, but it's still somehow intriguing that different types of objects are related to each other. And maybe it's going to be a giveaway to prove things like higher point dispersion relation, do a higher point S matrix bootstrap. That is very much still open question. Yeah, those are example of questions. Okay. So, yeah. Yes, can I take 5 minutes to? Yeah, great. Yeah. So in order to sorry about that. I want to break the spines. So I'd like to take a few minutes to move to the next topic, which would be the Schwier-Keldysh formalism. And it will be short because I basically already did it without telling you what it was. But in many situations, it can be useful to, instead of just looking at diagrams and drawing colors in a diagram, in many situations, it can be useful to have an actual path integral representation of these objects. Yeah. Oh, please, no problem. Yeah.
I should have asked this earlier, but so in the context of tree-level amplitudes,
Yeah.
does this discontinuity become a residue?
Yes.
Does cut become residue?
Yeah, that's a great question. So actually, this discontinuity become a residue of the pole, but you would only be able to access it if the particle that you're exchanging is heavy enough to be produced by the external legs, which means technically that it's unstable, because if you can produce it, it can decay. But you could use it, for example, in a tree level in a narrow width approximation for resonance. You would have a cut. That would be a way where a cut of a tree level propagator arises.
Thanks.
Thanks. Yeah. So sometimes it's useful to have a path integral representation of what we're computing. And so this is actually something that people have thought a lot about. And there's actually a very elegant solution, is that you're all familiar with the idea that we can write a scattering amplitude going from the past to the future by doing a path integral over this time contour with the usual epsilon minus I infinity. So t goes to minus I infinity with a positive imaginary part, goes to the future. And well, in order to compute these products of amplitudes times complex conjugate amplitudes, the solution is that you need to add a path integral that computes the complex conjugate amplitude. It's just a path that goes backward in time. So we have this time-fold picture that follows this contour. This is known as the Schwinger-Keldysh formalism. And you see that naturally you have a double set of fields in this path integral. So the path integral, I will label them as type 1 and type 2 in Roman, because I have so many subscripts so far. So the path integral becomes simply integral over the fields. Now you have to integrate over two sets of fields. And your action involves the usual action for the fields on the forward fold and complex conjugate, so basically minus I s of phi I to phi 2 on the reverse branch. And now we can insert various fields we want. If you want to calculate some product, you can calculate it like this. In general, if I insert some product like this, let me put the index here would be the position, and we put, say, phi 3 on the second fold, phi 4 second fold. So this is the path integral. You can use it to calculate correlation function. Here I'm taking an example of a correlation function where I put two guys in the first fold and two other guys in the second fold. And this would give essentially the vacuum expectation value of 1 and 2 are on the same branch. They get time order as usual. And what happens essentially is that the operator ordering follows the fold. So 3 and 4 end up anti-time order, exactly as you would expect for a scattering amplitude. Okay. So you can use this path integral to calculate this type of correlation functions. And one claim is that basically these LSZ reduce, if you compute this funny correlation function and you apply LSZ reduction formula to them, you get this sort of non-time order amplitude. Okay. The formula is a little bit I'm not going to write down the formula, and it's slightly subtle, but if you want to see it, it's written in the first of our papers. Okay? One reason this can be useful, why? So next lecture will be about using this formalism. So why it can be useful? Well, one motivation is that the formalism is very nice to study classical limits, for example. Like the path integral is almost invented to study classical limits. So if you're in a situation where somehow a classical limit is useful, is natural, could be useful. It can be useful to think about effective field theories. We love the path integral when thinking about effective field theories, and maybe to think also about IR divergences, as in Fabrizio's lecture. We introduce these funny observables there, and we could ask what are the infrared divergences of these quantities. And to do this, you would end up with something like collinear modes, soft modes, and so on. But what we propose in the paper, and we check in some examples, that we think about these soft modes and collinear modes along this contour. You can predict the divergences of these quantities. Divergence, so give a useful perspective on this sort of questions. And maybe the last motivation is that it's really essential. If you want to think about objects that have a finite temperature, or objects that have a complicated structure that you can excite and dissipate, essential for example, scattering of black holes, when you include effects where they can absorb energy, things like this, or finite T, or dissipative effect. And yeah, maybe I would just sketch here why this formalism is very nice in the classical limit. In the classical limit, what happens is that, loosely speaking, your field have a large classical value and small fluctuations. So that means that the average field, if you take the average on the two branches, that's the classical. But if you take the difference, phi1 minus phi2, that's order h bar. So fluctuations. So this formalism is very nice to take the classical limit. And I can erase this. So in the classical limit, this action becomes simply, and usually there's a 1 over h bar in the action, if you remember that it's not equal to 1. And when you expand this action in order h bar, you get simply x of I times integral of, you get the difference field. You only have to keep to first order indifference fields, and then you get derivative of the action with respect to the field evaluated on the average field. So the difference field just becomes a Lagrangian multiplier that enforces the classical equation of motion for the average. And this is plus order h bar. That satisfies Euler Lagrange, yeah, classical equation of motion. Okay. It's a very nice feature of this formalism that can be useful sometimes. Okay. So we'll discuss a bit more of this formalism after the break, and give you some exercises to play with it. Okay. So the best way to learn it, it's just to do some exercise. Yeah. So that's all.
Are there any more questions?
Hi. One question. Could you explain a bit about what's the difference between the different time folds and different Poincare patches?
Oh. This is a relation that is very specific to CFTs, conformal field theories. maybe it's best to discuss this in private.
Yeah, sure.
Because
Okay.
it's a, yeah, yeah.
Okay.
There's an interesting relation between physics on the cylinder and conformal cylinder and this time force, but yeah. Okay.
Any other questions? If not, let's break for coffee and we'll be back at 10:45.